Early access backer stream. Something. I don't know. No, shut up. All right. Start in a minute. Good morning. It's not even daylight outside my window yet. How ridiculous is this? How ridiculous is this? Testing, testing. Okay. Let me check my recording device levels. I don't know how this works in Windows anymore. Device properties. Like this doesn't seem to say that my microphone's ever peaking, but I have to turn it down in OBS, so I wonder. Levels 92. Looks like that's a copy of the OBS level. Is OBS like multiple? What? Dude, I don't know. It doesn't look like. Doesn't look like anything crazy is happening there. I just, I was listening to the mic volume on the YouTube video and it sounded really harsh. But it really doesn't look like it should be wrong. So, I don't know. It's computers. Did I stay up all night? No, but I slept for a while and then I woke up. Yeah, this may not be a long stream because from not sleeping enough, I may just go get tired and go back to bed. We'll see. But until that happens, I'm going to pick up where we left off and go. We've got more optimizations to do. Look, it takes more than 1 second to compile our game. That is not a situation we want to put up with. Yeah, this is totally the benefits of working from home, dude. You just get up, you go 10 feet into the next room, you turn on your stream. No, stream's starting. The stream is not over. Later, will I also try to optimize the time that the game takes to start? Yes. I have been feeling that it takes a little bit long. It might be hard to do things about that, though. We'll see. Why is there such a delay from when I press enter to when the text starts printing? What, here? What are you talking about? Oh, you mean this? I don't think there's much of a delay. I mean, the first two lines come out right away, and then we're compiling, and then this happens when we're about done compiling, which is 1 second later. It all makes sense to me. It must be strange to be able to summon a crowd of 100 people to watch you program any time of the day or night. It's pretty fun, except when people are annoying on chat, which is usually not. And in fact, on the rare occasions when it's annoying, it's like 1 or 2 people being annoying and everybody else is totally great. So, yeah. Anyone else getting black screen? Well, Twitch is a web program, and so it can't be expected to work properly. I would suggest reloading the page, because on the web, reloading the page is how you attempt to make things work. Well, when we last left off, we were optimizing the compiler because slowly over time, this number of how long it takes has been creeping upward as the program got bigger. You know, when I first demoed this program with the compiler, the program was like 60,000 lines. Now it's almost double that. And our compile time's been getting slower, so it was time, now that we've got more real code, to go look at why it was slow. And we found a lot of low-hanging fruit. And just in a few hours in the previous stream, we cut down the time from 1.65 seconds to where it is now. So we saved like a half a second, or like almost a third of the compile time. But we weren't done. We were just in the middle of optimizing a bunch of things. The things that I'm hitting right now are, they're not necessarily the biggest time bottlenecks on the board, but they're the easiest ones to eliminate because they're completely needless. And I have more ideas about things that are completely needless that I came up with since that stream. So we're going to do a bunch of those. And eventually, so this is, I mean, I've shown this before, but, oh wait, we're not even running telemetry. Let's run that. Windows decided to reboot helpfully between the end of the last stream and now, because why would you want it to stay running? So let's run another telemetry build to get profiling data. And, you know, so you can see we use a bunch of threads here, but most of these threads are not able to do anything most of the time right now. And even this thread, which looks like it has stuff, a lot of what it's doing is waiting on this thread. Not totally. Like you can see it's actually maybe cycling in here. This thread is always going to be slow. This is the thread that's like running bytecode or whatever. But, you know, basically almost all the work the compiler is doing, though, is this thread down here. And the part that we've been optimizing, well, part of what we optimized was name lookup, which happens all during this part. But what we've been working on during the last hour or two in the stream was this part, which is when we're putting together the object file for the program. And then this part is like we run the external linker and we're waiting on the result. And we're not going to be able to affect this very much right now. So this is just like a 0.15 seconds that we just eat. But we can do something about all the rest of this, right? So what we're doing is we're sort of working on this area. And, well, this pack data for type table, we can probably cut mostly down. But right now, if we go in here, a lot of these lambda body print disassemblies, which it's not really printing the disassembly, it's writing the object code, so maybe we should rename that. But a substantial portion of all of these consists of writing in address patch data, right? So here, you know, these calls to modify 4B, which are just very inefficiently written. They were written to just run initially and get us to a working compiler. They weren't written to be fast. So these are, I don't know, it's a good 30, 35, 40% of this time. This time here is very short, okay, but if that's like 35 or 40% typically, here it's less. Here it's about the same. Maybe that was a big one. No, you know, you can see that those modify 4Bs, okay, here's a ton of them. Oh, this is a long one. Anyway, we're going to cut a substantial amount out of this routine by hitting the modify 4Bs. Now there's also modify 8Bs in here somewhere. I don't know where they live right now. We know that we have a lot of modify 8Bs because when we take this profile view, we see them here. So we have modify 8Bs, and there's 24,000 of them. Each of them calls modify 1B 8 times. So we want to get rid of these, and then we want to get rid of these. I think we want to hit the 8Bs first. Even though it's easier to see the 4Bs in the profile, I think the 8Bs are still having a bigger impact. So let's do that. There's so many things to do to improve this compiler, man. All right. Well, let's take a look at things. So let's just look for people who call modify 8B in a loop, because I really don't know where that is. And I'm not sure, telemetry might give me a way to search down for that, but I don't know how to do it. I'm wondering if it's not even in this part of the program. I'm wondering if it's somewhere else. Those are all 4Bs. See, I keep finding the 4Bs. Where are the 8Bs? Look at all the 4Bs. Bro, I don't modify 1B. Lots of modify 1Bs. Actually, is this even... Yeah, that's up to date. Because we got rid of some modify 1Bs last night. All right. Let's just see which of these look like they get called a lot. So, type table packer has some modify 8Bs. Let's look at that. Where's that? Emit type table strings. Emit struct member data. Who calls this? Pack data for type table, right? That's 12 milliseconds, which is not nothing. Okay, where is that here? It's like... That is called from main. There it is. Oh yeah, it's 40 milliseconds, including children. The 12 milliseconds is just the self time. There's our modify 8Bs. Look at all those. Look at all those. So like every single one of these is a modify 8B. And it sure looks like that's the majority of that 40 milliseconds. So let's attack that. And again, this is going to be a little bit overstated because of profiling overhead. But, you know, especially because the modify 8B is instrumented and modify 1B is instrumented. But we're still going to party on it. Okay, so pack data for type table. Dude, my editor's been closed because Windows just said, hey, look, I know you're working hard, but what'll really help you is if I just restart and all of your state gets cleared and everything you were doing just gets wiped away and you can have a fresh morning situation. That's what Windows was thinking. Yeah, modify 8B is a pointer patching operation, you know, where you know, you need to write in a pointer offset or something, but you don't know where it needs to point to yet. So you save the location. And then later you go back and you write the location. Now, the thing that's making that slow right now is that the place where this data is being stored is in this data structure called the concatenator, which is like a bucketed buffer of bytes, right? So every bucket is 64K. And you just write data. And so that we don't have to like copy the data by resizing it contiguously or whatever. We just add a new bucket when you overflow that 64K. And then however big that ends up being, that's how big it is. And then we write that sequentially to a file later. So in principle, it's all good and fast. Now, the problem is when we store these locations and then later come along and say, modify these 8 bytes, we've been being very paranoid about it, because we don't know if those 8 bytes cross a bucket boundary, right? So you can't just stomp the memory. And in fact, you don't know what bucket it's in because you just have the index of the offset. So we have to start at the beginning of the thing. We have to count forward till we find the right bucket. Once we find that bucket, we have to find the byte offset within the bucket and then search. And rather than do that in a very paranoid, or rather than do that in a very optimized way, because I knew this was temporary code, I'll show you what this looks like, and it won't be any secret why it's slow. Here's what it looks like. This is doing endian stuff. We're masking off bytes in a specific order. And then calling modify 1B with every byte. It's ridiculous. Like, yeah, the compiler is probably doing some stuff to optimize this, but come on, right? This is all just to write an 8-byte integer into a location, which most of the time you could do in one instruction. So in order to make it so that we can do that in one instruction, what do? Well, when we put the thing into the concatenator, if before we put it in, we say, hey, let's make sure, let's reserve enough space that we don't cross the bucket boundary. Let's reserve 8 bytes. And if we can't, just go to the next bucket right away. If we do that, then these patching operations don't have to do this because they don't have to worry about crossing the bucket boundary, right? And then, you know, of course, we can do a much faster endian swap, which is a no-op on this machine anyway, because we're little endian and we're storing things little endian. And, well, if you also are guaranteed that the memory of the concatenator isn't going to move, then you don't need to use the integer index. You could just save a pointer. And so that's what we did in the previous stream. Anyone who wants to see the earlier work on this can go look at the VOD. It's going to get uploaded to YouTube later, but we did this a number of times last night. And just this optimization gave us 0.16 seconds improvement so far, and we're not done doing it. Yeah. What if the bucket size is less than 8? Then you fail. You fail at life if your bucket size is less than 8. Okay. So we have to just look at the cases where we're doing this. All right. Modify 8b. So when we're emitting strings, all right, there's this thing called string to emit, and we save the pointer location in the buffer. And if this is the only place that uses that, then instead of storing this, we would store just the pointer. However, I think other people might be using this. We needed, yesterday when we did this optimization in some other places, we needed both the target memory and the integer position. And the reason we needed the integer position was because the object file actually wants that when you're writing the relocations into the object file. Now, the other thing is that I realized while I was not sleeping is when we get this position in buffer, that's even slow because we're calling concatenator length, which is adding up all the bucket sizes. We can also optimize that, but we're not going to worry about that yet. We're going to get rid of all the modify B's first. Bucketing can be dangerous business, it's true. Okay. So we've got this one. This is with strings. I assume somebody else uses that. No, it's just type table packer. And it's just strings to emit. All right, it's a lot of code just for one simple thing. Okay, so there's that. That doesn't look hard. This is for string literals, which we're not really... Well, okay. I'm writing down more ideas of stuff to do. There's so much stuff that has just been done just to be slow, right? Or whatever, just to be basic. And there's so much low-hanging fruit to make this faster. Okay. This is an array of strings. We're not going to worry about this one yet. Actually, these two, we can do these second. This is only for type info for enums. There's an array of names and an array of values, and these are like pointers that tell you where the array data is. We can optimize that, but this doesn't happen that often, so it's not that much of a priority to optimize that. We could maybe optimize it later, just like eventually we want to get rid of modify 8b maybe, right? Just to reduce our code size, and then we would want to hunt these down. But this is not really going to change our performance right now to do those ones. And that's it. So we have this one, that one. Okay. So there's two that matter and two that don't matter in this file, I think, is my theory. Okay, so when we set pointer location in buffer, we will see, we're also we've got our string to emit, right? But then we've got a general, like a patch that we're telling the object file that there's a pointer here. So these are both, yeah. We might be able to simplify this later. I don't know, man. Yeah, I think that's it. Okay, so here we're gonna stuff the pointer, but first we're gonna store the pointer. So here we're gonna say I'm forgetting the names of all these things. Ensure space and return pointer. Yes. So target memory equals to emit ensure space and return pointer of 8, right? And again, I'm going to write that down. Like, we should just make a very specialized one that's like ensure 8 bytes and stuff an 8-byte 0, right? Because that's almost always, well, we're going to want a 4-byte version of that as well. Anyway, I wrote down to optimize that even. Okay, so we get the target memory. Because we did this, this will make sure that we don't cross a boundary, right? So to emit.target memory equals target memory. Just going all over the place. String to emit. Void star. Okay, let's just compile that. Because, like, ensure space and return pointer is not, yeah, that's not a member of string to emit. That's, what am I thinking? What am I thinking? I'm not thinking. Let's not be in telemetry build right now. Dude, C++ compilers are so slow. It kills me, dude, how long this takes. Literally, I'm growing old right now. Holy shit. All right. Okay. We still appear to work. It's no surprise because we didn't change anything yet. In fact, we just made our program a hair slower by having it store more data. All right. Great. Great. So here, let's go back to this. Right? So we just did this in all our things, and we're going to do it here. And what was our tag that we said? We're just going to put a little reminder. Type info patch. It's just let's just make one, right? So instead of modify 8b, we're going to say this. And, well, it's not lambda address, it's just address. Now, this length here is slow, like I was saying, so we're going to want to optimize that. But not yet. Because we're getting rid of the modifies, not the lengths yet. We're getting rid of the modify B's. Illegal indirection. Yeah. Let's make it an S64 like I was gonna. Right. Yeah. All right. All right, we know how to program maybe sometimes. One 108. Look at that. 108. 108. 109. 110. Ugh. 109. All right. Does it run? Does it blend? Yep. Okay. Okay. So that's great. Let's do the telemetry build and see how many modify 8Bs we managed to get rid of. I bet there's still quite a number. That, I think, my theory is that that was the majority of the modify 8Bs in type table packer, right? But there might be other ones in the object file writing process. Let me close some of this stuff. Okay. 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 Boop. Boop. 705. Timeline. Let's just get this profile. Oh, that's the wrong one. This profile. I was like looking at it like I don't see. Okay, so modify 1B. We're down to 178,000. Wow, we really kicked its ass. Now the funny thing is, like I was saying, most of these type table entries that we're calling most of these modify 8Bs, eventually we're not even going to pack most of them. All right, but for now, while we're packing them all, we might as well make it as fast as it should be. So like modify 8B is like not even like. There it is. It's way down here. We have 2,000 of those. It's still taking a millisecond. I'm going to put an eliminate modify whatever B completely out of the program so that we can delete the code. And maybe we won't grow quite as old while we're waiting for it to compile all the time. But it is now no longer so important to chase down the modify 8Bs. Now we want to chase down the modify 4Bs. Because now those are calling the majority of these modify 1Bs. Right? And we saw where those modify 4Bs were. They weren't hard to find. I mean, Lambda body print disassembly has a lot of them. So let's do that one. Print disassembly. That's really not the right name for this. This is not printing a disassembly, it's outputting machine code. Let's rename it. It's better to rename it than to keep saying it's not the right name. Okay. Output machine code. Well, who's modifying 4B? And jump patches for current bytecode. Apply symbol patches. That's it. There's only 2 in this entire file. And this is the one that's in this routine that we keep seeing. So it's just 1, bro. So jump patches for current bytecode. That's a jump patch. Pointer location. Okay. Void target memory. S32 star target memory. Okay. Well, where do we put these together? Jump patch. That's it. Right? Is this the only file? Whoops. Jump capital patch. Yes, it's the only. We got so many patch types, dude. Maybe at some point I have to consolidate these. It wasn't clear whether it was better to have them all be separate or together. I don't know. I don't know. Okay. Literally, we call this in 2 places. All right. We want our target memory variable to get assigned and passed in. Right? And again, these lengths are slow also. But we're not doing those right now. We're just doing the other thing. Okay. So in x64 instructions, we have these. We also have jump relative 32. Why don't I put the 32s together? Okay. Add patch for jump to bytecode instruction does not take 3 arguments because it's C++. You can't just... Look, if you're programming, you can't just add the argument. And in fact, because we're in C++, you can't even just add the argument once. You can't just modify your procedure declaration to have an argument. You have to go then add the other one, because that's how programming is in the year 2018. All right. Oh wait, we rebuilt the telemetry and we ran the release, so that's no good. Who's zero bagging? Don't zero bag. All right, 1.1, 109. Seems like this didn't affect our runtime at all. Oh, because we're not using the pointer yet. Of course it didn't. In fact, of course it made us slightly slower. This is fine. Let's make sure we still run. We're still running. We're still doing our things. Yeah, baby. We're walking. We're mirroring. All right. So we're not actually using it yet. Jump, patch. Oh, jump patches. Okay. Instead of this, we're going to do this. Byte swap 4. Target memory is S32 relative. Uh-oh. We screwed up. We screwed up. Interesting. What did we not do correctly? I mean, that's the same thing we were doing for all the 8-byte ones. You forgot to assign memory location to the jump patch struct. I don't think so, because it would crash if I forgot that. Oh, wait, what? This is what happens when I don't sleep, is I just say patch.targetMemory semicolon. How did this even run? Oh, it didn't, right? Okay, I understand. So this here, This assertion failed is probably our null pointer trap going off, and that's new. Like Ignacio added that, so I'm not used to seeing it. So I figured that this was an assert later in the system, but really that was us dereferencing a null pointer because we forgot to set the thing. You know, so some people ask me, how do you get in the game industry? And how do you really become a good programmer? And how do you design games that are sophisticated and that people want to play? And then how do you get the guy from Kotaku to stop eating his cheeseburger and look over at your game when you're at PAX and there's a crowd shuffling by and nobody's looking at your game and you're sad? And I say, don't type patch.targetMemory semicolon. If you do that, you're not going to succeed in the game industry, okay? Because that is not the right code. Don't type that. That is my most useful advice to people. Do not type patch.targetMemory semicolon. Okay, well, apparently it's still not good enough. Wait, what? Didn't we just run it a second ago? How did I... Okay. Now we're really sad. Okay, I don't know what happened there, but oh, no? Okay, what happened is we're kind of inconsistent here. We're working sometimes. Yeah, and that time that we even thought we compiled, we don't run. So it's still wrong, you know? And then I tell people, even if you don't type patch.targetMemory semicolon, you still may not make it because it's a tough business, you know? Is the industry changing that fast? Yes, it is. Yes, it is. Okay. Well, we could certainly, you know, we can do the thing we did before where we do the modify 4b and then we assert that the contents of target memory are equal to that. And that'll at least let us see what is not correct. And who knows, right? So assert that. That should go, if that assert doesn't go off, then I don't know what the hell is going on. Okay, it did. It did. So let's see. Why are my windows all screwed up? Dude, this compiler sucks. Debugger, whatever it is. Okay. Okay. The target memory is there. Pointer location, instruction index. Okay, well, it's not even 64K into a buffer, dude. So, like, this should be the easy problem. It's got some data in there, but it's not the data we want. So, well, we must have done something real dumb. Let's double check this. I mean, this looks fine. This looks fine. This looks fine. Okay, so we're here. We have this. It had better get assigned one of these. We pass it. Those don't look wrong to me. So well, there's another assert that we can add. So at the time when we do this, what was it called? Okay, wait a sec. No? So let's look at, since this is in the first bucket, it'll be real easy. So output Oops, that's not the right name. Oh, it is. Output dot last it wanted. Okay, so output last start output dot last arrow start plus it dot pointer location is this 20E5 D900. Target memory is not that. Target memory is D8F4, which is 12 bytes off. Why? What, 12 bytes? That's a long way to be off. Why are we 12 bytes off? What, 12? I mean, I would understand 4 bytes off, or 8, but like 12 is banana cakes. Last point minus 4. What are you guys? Oh God! Thank you. That's what happens. Sometimes I don't even know what you need to do to succeed in the games industry because it still doesn't even work. What are you guys telling me? Oh, that was the debug build. Haha. Compile release build. Okay. If you're going to succeed in the game industry, I think I've said this one before, compile the release build and then run the release build. Otherwise, you can't release your game. Unless you release the debug build like the PUBG developers and many Unity programmers. That didn't save us a lot of time. It saved us a little bit, but I wanted to see the number go down more than that. So I think we have more Modify 4Bs to attack. Yeah, I didn't get enough sleep. It's for sure. This is what happens. You know, you don't get enough sleep and then you make a little mistake like that and you pay for it. Yeah, pay for it. Okay, let's check in. Let's run tests and hope we don't hit our stupid Heisenbug that we've been passive-aggressively avoiding fixing. All right. Yeah, well, we still get it, but it's fine. We're living with that for now. Calls. Okay. Now the funny thing is, all these we like get the length and subtract 4, and then we just add 4 later anyway. So this is another thing that we will want to fix. Okay. Let's look for more modify. Oh wait, that was, we were saying that that was the only Modify 4B in there. So I'm actually shocked that we didn't get more time than we did out of that. That was weird. But that was the Modify 4B that we were seeing when we zoom in. And maybe that wasn't the most common one. Let's see. All right. Let's see what we got here. 729. We've still got Modify 4Bs. Oh, cause I didn't, bro. If you're gonna do it, do it. You know what I'm saying? Do you know what can you smell what the Rock is cooking? I'm shocked that we didn't get more time out of that optimization. I'm completely shocked. All right, 109. 111. We still didn't get that much. 107. Oh, we got a 107.9. We didn't get that much. 107. Okay. Now it's okay. Yeah, it's smaller. It's smaller. This is what happens when you don't sleep, though, man. Of course, I did that same thing last night. If you watched last night's VOD. So, wait. Why didn't this? I don't trust this. Why didn't it frickin' rebuild? Might you suggest the Unity 3D engine? Actually, I do that a lot. Yeah, I probably do that a lot. Okay. All right. Let's close these old ones. We don't need them. Boom. 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 Timeline. Look how small this is getting. I mean, it's not a lot smaller, but it's getting smaller. Okay, so now when we zoom in here, we don't see a ton of Modify 4Bs. Note branch target buffer position, that's slower than it should be, but it's not, like getting rid of that is not going to be huge. So let's see who, I bet there's more Modify 4Bs though. Modify 1B, 90,000. Modify 4B, 18,000. So this times 4 is 72,000. So it's still most of the Modify 1Bs. 8 milliseconds, you know, but with overhead, so who knows how many milliseconds it actually is. You know, at this point, I mean, we're talking about shaving 8 milliseconds off compile time. which isn't going to affect it that much, but we're going to do it anyway. I mean, look at all these milliseconds. 8 isn't going to matter that much, but we're getting toward the end of this optimization. That is, where is it? We don't actually know where that is. It's like not in the place that we've been looking. Is it here? Yeah, modify 1B. Oh, modify 4B. There we go. Patches for entry points. I mean, that's 27 milliseconds, and it looks like it's mostly modify 4Bs. Oh, 8Bs and 4Bs. Oh. Okay. We still got 2008 Bs, and they're in there. Okay, well, we're going to do that one then. Hopefully. Patches for entry points. These aren't entry points of the program, they're for procedure entry points, so there's a bunch of them. Okay, modify 8B, modify 4B. This is basically the same as this other one that we did yesterday. Patches for entry points. That's an entry point patch. We just didn't do this one. Okay. Well, you know how this goes. This is the only one. Okay. Actually, this comment here was wrong, that this is temporary. This is not temporary. Okay. Entry point patch. Okay, because it's C++, you have to do everything twice. When we call this, we need to pass the argument. We passed a null there. This is the only other call. And guess what? We already have this, so we could just do that. And we need our cast again. Cat being castigated for not having our cast again. All right. There is an advantage long term of writing the compiler in its own language, and that would be that we're going to do some stuff that helps with thread safety in terms of writing programs that feel more secure in terms of not having thread bugs. But we haven't done those things yet anyway, so so really it would just be a matter of being happier. All right. Let's actually see if that runs. It shouldn't matter. We didn't actually change the value poke, right? Now let's change the value poke. Entry patches for entry points. Okay. Instead of this, we're doing our old thing. Ba-bam. Well, if this fails, we ain't going to be calling any procedures. So it better work. 109. 108, 109. Yeah, I mean, it's not really... We started out tonight at 111, so 109 is not that bad. But today, not tonight. Hey, we're calling procedures. We got a stew going. All right. Well, let's get rid of the modify 4b that's down there. Okay, let's actually make this oh no, S32. I was gonna break it. Don't do that. Dude, modern C++ people are having a complete aneurysm when they see me type this stuff, by the way. They are freaking out. They're performing exorcisms on the YouTube video. Let's actually make this be void star. Whoops. Otherwise, all right. So, yes. Let's actually, since we're doing a lot of things at once here, let's leave this for a second and we'll make this compile. We need to save the target memory for this. Add patch for entry point. I don't know, why is it not called add entry point patch? Because it's C++, I have to do that twice. All right. Okay. Add entry point patch. Target memory is call relative 32, target memory. Okay. This is no longer true. I don't know why I bothered to type that comment. because I wasn't sure what I was doing. That's why. Okay, so we need to make call relatives 32. Can you pass to avoid star and not cast? Oh, it's S64 star. Let's not do that. Add entry. I'm getting hungry. I'm getting hungry. We might do a stream break while I go get breakfast. We've been doing so good, I could treat myself by going next door and getting a nice breakfast. Compiler is an entire almost 0.6 seconds faster than it was 12 hours ago, or yeah, we'll call it 12. All right, well, we're compiling. 112. Oh God. Okay, we don't expect any speed up because we're still modify 4Bing. 4B or not 4B. Okay, so okay. How is this compiler different from the Linux compiler or OS X compiler? We run the same code almost completely. There's an operating system interface layer that changes. 107, 109, 106, 107. We're putting away better numbers now, man. I like seeing a 1 with a 0 after it. That feels like an okay neighborhood. It feels like we're eventually moving on up to the east side. Moving on up to the east side. That's probably about as long as it takes the Visual Studio compiler to start up. We compile our whole program. I mean, not really, because obviously it starts compiling, but if you add the startup time for every single one of these files together, I bet it's about 1 second if you do a full build. All right, telemetry build. Sham bam bamina. Timeline. Look at that, it's so tiny. It's so tiny. Look, this is, okay, this section here is us making the object file. This section here, I guess we don't have a time on this, but you can see it's almost as wide. It's smaller than this one, but not that much smaller. This is us linking this entire thing that we just outputted. It takes almost as much time to link as it did to output. It doesn't make any sense. It doesn't. Why do we do things this way? It doesn't make any sense. When we can get away from the linker, we're going to be so happy to do that. Okay. And that's dynamic linking. That's not even static. If we statically link, it'll take frickin' forever. Okay, I don't really see modify B's on here. I see some. Here we go. 5,000, 600. I'm liking these numbers a lot more than the old numbers. Modify 1B still has 15,000. It's not a lot of milliseconds. Modify 1B is really very easy because you're guaranteed that 1 byte doesn't cross a boundary. So we might attack some of those just to do it. Like, I don't know. I don't know where they live though. We can just search for them in a file. Modify 1B, modify 4B. Prepare code and symbols. Is this all modify 4Bs? That's like, oh, well, when we zoom out, it's not very much of that 29 milliseconds. I mean, it's not negligible, but it's like 8%. It's like 2 milliseconds. Yeah. We could do that though, because I don't know. Let's just look around. Dude, my computer is running its fan. Okay, there's no more modify 4Bs in this file, so it must be an obj writer. Section headers. Those happen a very small number of times. Okay, string table. I don't know what the difference is between that Linux and non-Linux code. I don't understand, but it's fine. So we actually have a lot of modify 4Bs, but they're not really a lot because they're not in loops. So this is for a dwarf file. Look at all these concatenator lengths, dude. Yeah, that's something we're gonna want to fix. That's going to buy us some time, I think. All right. There's no modify 1Bs in this file. They're all here. They're all branches. There's only 5. Okay, 2 of them are in duplicate array elements. I don't think those are going to be the most common ones. I think they're going to be array bounds check. I feel like they're going to be array bounds check. So let's hit that one. All right. Post branch A. Okay. Call it target memory because that's what we call everything else. Okay. So instead of this, we're going to say this. Hope we didn't screw that up. And again, this is, there's all these redundant things happening here, but yeah. Okay. Well, branch B target memory is, you don't need byte storage branch A, right? Yeah, that's gone. You don't need this. Okay. Oh, target memory. Branch B distance. We must be doing a lot of array bounds checks. It's not too surprising. So if we have about 15,000 and we have 3 per array bounds check, we must be doing 5,000 array bounds checks in our program. That sounds reasonable. All right. Branch C distance. Well, branch C. Yeah. Post branch C, byte storage branch C is, no. Wait, really? Whoa, we did the wrong thing. We didn't crash, but we did the wrong thing. This is branch C. This is branch B. Emacs. This is branch B. That was, see, sometimes you optimize and you actually do not optimize. Okay. Okay, that was very bad. We should actually test some array bounds checks and make sure they still work after we're done with this. It's not good enough to make sure our program still runs. We need to make sure that we're catching array bounds check failures. Okay. Okay. If we just turned off array bounds checking in our builds, it'd be under a second. 108. 106, 106, 108. So much fluctuation in runtimes. I'd call it 107 right now. Oh, 105.6. 115. Oh my God, stop fluctuating. I'd call it 1065. That's pretty good. So we've saved like 45 milliseconds this morning. It's a good thing I didn't sleep. This is a full recompile. How is that even possible? Even reading files should take over 1 second. No, it shouldn't. This is what I keep saying, okay? Modern software is so crappy that people have no idea how fast computers are. Because you've been trained, like you learn how fast computers are by just seeing how long they take to do things. You've been trained to think that computers are hundreds of times to thousands of times slower than they actually are, okay? This 1 second to compile 100,000 lines is pretty slow because it's mostly single core performance. So all we have to do is parallelize and we can divide that number by 6 or 8. I mean, parallelization is hard and a lot of work, but we can do it, right? What we're doing right now is just low-hanging fruit for single core performance, and we can still do a full build in 1 second. That's how crappy and slow all your other software is, okay? is that we're being crappy and slow and we compile in 1 second. People, I try to communicate this to people and they just think that like, you know, I'm some wacky person with strong opinions or something. But no, like computers are wasting your time every day, all the time, forever. Forever. Computers can do computers can do a lot in 1 second. Dude, this compiler is so far from how good it could be. Like when we go look at this telemetry profile, right? All of these threads, like what you would ideally see is all this work here chunked up into like 6 or 8 equal parts. I forget how many cores I have on this computer, but like, you know, so that's a half, that's a quarter, that's an eighth. You should see this whole thing take place in that much space, just piled up the screen, right? That's the ideal. Or actually smaller than that, because a lot of this work we're doing, we still don't even need to do. There's plenty of low-hanging fruit optimizations to do. So, yeah. You want to add sleep 1 second so people don't get scared. It's true. It's true. Is the bytecode SSA based? It is not SSA based right now. I'm not sure if we should do SSA later or not. Like many things in compiler land, I'm not sure that SSA is really necessary or a good idea. Just because everybody does it doesn't mean you should do it, as your parents would tell you in the 1950s. But that's not me saying it's not good either. It's just I haven't really done the analysis, right? And I imagine, yeah, like, so one reason we don't do it right now is because we don't, for this build that we're doing in 1 second, we don't do any data flow analysis on this, right? This is just outputting x64 code in the dumbest possible way, which is one reason why it's fast, right? If you want optimized code, we give that to the LLVM backend. LLVM chews on it for a while, and then you get optimized code. At some point, we probably will do some data flow analysis, because some amount of data flow analysis will probably make the compiler faster, because if you're not generating this nutty amount of instructions, then this will go down proportionally. The question is, can we do a small enough amount of data flow analysis that it's a net speed win? And I'm not sure. We have to look at that. Is there a time benchmark we have in mind? My goal is 1 million lines of code per second. So 10 times as fast as we are right now. So we're back up to 100,000 lines per second. I didn't realize that. We just made this benchmark approximately, right? So we have, I just said 1065 was what I was eyeballing this, and we have 1067. So we're back at 100,000 lines per second. Of course, that includes white space lines and whatever. So if you filter those out, it's less than that. But, you know, just as a ballpark. And we should be able to get 1 million lines per second. And by the way, this is with debugging instrumentation and like array bounds checks and stuff. If we turn that off, we'll go faster. I mean, this is with all this messaging happening where your meta program in frickin' slow ass bytecode reads all these messages about what's in your program and decides to modify it, right? Like we're doing all that in this 100,000 lines per second. At work, your Dart compiler takes 20 minutes to transpile is 2KK 2000 or 2 million? I don't know. 2 million. Okay. So it's 1 million lines of code in 10 minutes. So it's 100,000 lines a minute. And it's transpiled to JavaScript, so that's going to be great. You were thinking of ditching AST in favor of SSA because by looking at the code that handles type checking, it is doing a lot of stupid things. You're wondering if it's a good idea. Ditching AST, I don't know exactly what that means. Like, would you parse directly into SSA form? I don't think that makes sense. Because your SSA is going to depend on what your types are. And you need a phase where you figure out what your types are. In this compiler, the phase where we figure out what our types are is doing most of the work. That's these green sections that you see here. It's a lot. Handle run pipe, yuck. If 1 million lines of code per second is the end goal, what do I aim for the beta release? Well, for beta, I honestly would be happy with this current speed. Because, 100,000 lines per second is pretty okay. But since there's so much low-hanging fruit, I'm not going to stop right now. We're going to keep pushing it lower. But if we fall back to this speed of 100,000 lines per second for the beta, I'm okay with it. But we should be able to do over 1 million lines in the final compiler, no problem. Would I consider buying a 60 FPS webcam? I think this webcam might be able to do 60 FPS. I'm not sure. Maybe not. Ghost Goats Games is hosting us, but we're about to sign off and get breakfast. But we'll do some more later today. I think, okay, let's just take a look. We're going to have a lot of profiling overhead, but I want to do concatenator length. Because I think this is eating a lot of time. Because like we iterate over all the buckets and we add this together. And we're doing this basically everywhere that we were doing those modifies. So we should be able to get an equivalent speed up in every one of these places. So let's just do this. Oh, that's release builds. Oh, I don't think I checked in. Oh, and we didn't test our array bounds checks. Okay. We'll do this and then we'll test our array bounds checks and then we'll sign off. Are these compile speeds the same across platforms? Yeah, nothing that's tremendously OS specific is happening there. I mean, the file format for Linux is a little bit different, but we're doing the same sort of work. So the optimizations that I just did apply to all platforms. Am I planning on changing the syntax? Yeah, possibly. Can't I store a running sum of the total length whenever you append a bucket? Yes, that was my exact plan for how to optimize it. Well, and also though, some of the times when I say length, I don't need it and can just use the pointers. But yeah, exactly, right? I mean, the naive thing to do is just track the length every time you add something, but then you're probably paying too much. So you do it every time you cycle a bucket. Okay. what was I doing? Oh yeah, we were going to telemetry, concatenator length, and recoil and horror at how much it is. 807. $267,000 calls, 65 milliseconds. Again, this includes a lot of profiler overhead. I don't know how much overhead there is, but I don't think we should call that 267,000 times. So we're going to try hitting that a bit. Like, let's look at type table packer, right? Because we know that had I mean, those don't look that long, but in principle, as the data we're packing gets longer, they should take longer because they're iterating over more buckets. So if I look here, 200 nanoseconds each time. Yeah, I don't know what the profiling overhead of telemetry is in nanoseconds, so I can't really say, but I mean, we shouldn't be doing this. We shouldn't be frickin' iterating over all the buckets over and over and over. Okay, so these are, so toward the end, let's get the very end and the very beginning. Basically 200 nanoseconds at the end and at the beginning. Wow. We're real zoomed in, man. We've got some powers of 10 action going on here. 15 nanoseconds, yeah. So it gets a lot slower over time. I'm not sure what percentage of the total time it is. Yeah, that's still, until we start filling buckets, it's not going to take any time, right? So out here, it's like 13 nanoseconds. And you're probably still in cache most of the time until you have a lot of buckets. 100, yeah. So at some point, there's a cliff that we hit. We shouldn't really be doing that at all. In fact, we probably, in this case, could store a local variable. Oh, no. Okay, so in here, like these could all be unchecked. Like we could reserve space and then do unchecked here. Like all, dude, this whole thing, I mean, it's 25 milliseconds only, but by the time we finish this, it's going to disappear relative to its current size. And then, like I said, this is not even going to get called for only a fraction of what it's called for now. So, you know, that 25 milliseconds is going to completely disappear. And optimizations that are just as easy are all over the frickin' compiler. So, well, type inference is not that easy. Other parts, though. Okay, we're not actually going to try to optimize this because I'm trying to go to breakfast, but trying to go to Brexit. Yeah, so if we just optimize length rather than substitute these, that's probably the most effective thing to do. Yes, we're doing array bounds check testing. And I'm just going to do a dumb check right now. Going to go into main. Let's Sokoban. And we're going to say array is 3 floats, right? X is array sub 4. Okay, well, that is statically checkable, so we actually get that one during compile time. Okay, this is a runtime check. There we go. Index is 4, limit is 3, minus 1. Index is minus, okay, so our array bounds checks still work. Ever seen the new Blackout update? New map. I don't know if a new map can bring me back to Blackout. Maybe. I'll think about it. I'll think about it. Further optimizations. Back up to 100,000 lines of code per second. And that's even... That's for our... Don't we have like a fast build? Oh. That's what we do by default is fast build. Okay. But fast has array bounds checks in it anyway, so it's not as fast as it could be. Okay. Thanks everybody for coming by, and we'll do some more of this today. We're going to optimize that length probably next, and then I have some other things in mind. We can, so for all those things that we were adding, all those like 7,000 different patch data structures that we have that all have arrays, for almost none of those are we doing, you know, that array element add situation. We're doing a local stack copy and then adding that. So those are not going to be huge wins individually, but I think they'll be noticeable and they're easy. So we should do those. Ultimately, some of those arrays are growing and copying themselves a lot. So if we make a data structure like a bucket array, we'll stop spending time there. And then there's a whole thing with the atom table that we can do, which we'll talk about later. Thanks everybody for coming by. We're not going to raid anyone right now. We can't raid 100% of the time because then we're too predictable. I'm going to go to breakfast. Thanks for coming by. If you missed what we were doing, you can go to last night's video. Let me go link you. Last night we started this round of compiler optimizations. I'm digging up the video. Here it is. I'm pasting it in chat. So that sort of, if you want to keep watching compiler stuff, that shows you the origin of this current run. Again, we're just killing low-hanging fruit that takes time. And, you know, we started yesterday at 1.65 seconds. Whoops. And now we're down to like 1.07. So we've shaved off like, well, you know, of course it varies, but we shaved off like 0.5 something seconds, almost 0.6 at this point. So it's been very productive. Thanks for coming by, and I'll see you later today.